Okay, welcome to Chapter 13, Section 3. What is energy? Let's get right to the key ideas here. What is the relationship between energy and work? Why is potential energy called the energy of position? What factors does kinetic energy depend on? And what is non-mechanical energy? So let's move through the bell ringer here. Energy and work. What is the relationship between energy and work? Whenever work is done, energy is transformed or is transferred from one system to another system. So energy is basically the capacity to do work. Energy is also measured in joules, which is what we measure work in as well. They're basic forms of energy, and we're just transferring or transforming energy from one system into another. Just like if you're moving a box, you're transferring energy into that box just to move it. So potential energy. Why is potential energy called the energy of position? Potential energy is sometimes called energy of position because it results from the relative positions of objects in a system. So potential energy defined is the energy that an object has because of the position, shape, or condition of the object. So any object that is stretched or compressed to increase or decrease the distance between its parts has something called elastic potential energy. When you stretch or compress a spring, you're basically storing up potential energy or energy that is potential to be released at some point. So example, there's stretch bungee cord or compressed springs there. Any system of two or more objects separated by a vertical distance also has gravitational potential energy. So lifting something up to a certain height, if you let go of it, it has the potential to use energy, which it does in falling. So a roller coaster at the top of a hill, as it moves down that top of the hill, it's gaining speed, which is energy. So let's listen to this visual concept here on energy, potential energy.
Potential energy is sometimes known as energy of position or stored energy. One form of potential energy is gravitational potential energy. An object that is raised above ground level has work done on it. This work increases its energy. At the top of the slope, the ball is not moving, but it has the potential to do so. If it falls, the gravitational potential energy will change to kinetic energy. There are many other forms of potential energy. A piece of wood, for example, contains chemical potential energy that can be converted into heat and light when it burns. Increasing pressure along a fault line does work on the various rock layers and increases the potential energy along the line. This energy is released during an earthquake.
Alright, so let's move on here. Potential energy. Gravitational potential energy depends on both mass and height. And you should be familiar with that. Is the larger something is when you drop it, the more energy it has when it hits, or the higher you take something, the more energy it has as it falls toward Earth, which basically the more speed it gains as it moves through. So gravitational potential energy is mass times the free fall acceleration times the height, or potential energy is m times g times h. If you'll remember from chapter 12 where we did weight, weight was mass times g, the free fall acceleration. So in a lot of ways this is just weight times height for this. So the height can be relative. It depends on what you're measuring the height from. If you're measuring from a tabletop or from the surface of the earth, there are different heights that are involved, so it'll have different energy related to those heights. Alright, so mass skills, gravitational potential energy. So we have a 65 kilogram rock climber ascends a cliff, so he goes up a cliff. What is the climber's gravitational potential energy at a point 35 meters above the base of a cliff? So this rock climber has climbed up to a spot 35 meters above the surface of the earth, and the mass of the rock climber is 65 kilograms. So let's given and unknown values. So we do know that the rock climber's mass is 65 kilograms. We do know that he's at a height of 35 meters. Now, going back to gravitational potential energy, something it didn't tell us in here was what was the gravitational free fall acceleration, but because we know that it's constant on the Earth. Free fall acceleration is always the same. It's represented by the letter G, which is 9.8 meters per second squared. That's a given for us. It doesn't have to state that in the problem. So we have G is 9.8 meters per second squared, and what we don't know, or the unknown value, is the gravitational potential energy, and that's what it's asking us for. What's the climber's gravitational potential energy? Alright, so write the equation for the gravitational potential energy, which is PE is equal to mg times h, or weight times height again. Insert the known values in the equation. So we're going to insert, we know mass is 65 kilograms, free fall acceleration is 9.8 meters per second squared, and the height is 35 meters. So when you multiply those three things together, you get an answer of 2.2 times 10 to the fourth kilogram meters per second squared. 2.2 times 10 to the fourth basically being 22,000 kilogram meters per second squared, which we also know is a joule from our dealings with work. So 2.2 times 10 to the fourth joules is what the gravitational potential energy is. So let's go on to kinetic energy. What is kinetic energy, and what factors does kinetic energy depend on? Kinetic energy depends on both the mass and the speed of an object. It's basically the energy of an object due to its motion. If an object has motion, it has kinetic energy. So the equation for kinetic energy is Ke, so kinetic energy, is equal to 1/2 times the mass of the object times the speed of the object squared. And only the speed is squared. You do not square the mass or the 1/2. It's just the speed for this. So K equals 1/2 mv squared. Alright, so we have a visual concept here on kinetic energy.
Kinetic energy is energy of motion. Both of these cars are moving, so they both have kinetic energy. Kinetic energy depends on both the velocity of an object and its mass. Kinetic energy is calculated by multiplying mass by velocity squared and dividing by 2. If the red and green car each have the same mass, the red car has more kinetic energy because it is moving faster.
Okay, just real quick here, we said right back there that kinetic energy was 1/2 mv squared. They have it written the same way up here as an mv squared divided by 2. If you multiply something times 1/2, it's the same thing as dividing it by 2, so I don't want you to get confused there. This is the same equation.
Even though the truck and the red car both have the same velocity, the truck has more kinetic energy because it has more mass.
Okay, so the more massive an object is, the more kinetic energy it's going to have. The more speed the object has, the more kinetic energy it's going to have. Alright, so kinetic energy depends on speed more than mass, really, because it's squared. So the larger the speed, the more kinetic energy. You see here on the graph, velocity at 2 meters per second, you have 100 joules here. Velocity at 4 meters per second, you have 400 joules. So the faster you go, the more kinetic energy increases. It's an exponential increase. Atoms and molecules have kinetic energy. You should have seen that from, you have electrons and atoms that are moving around in objects. So they have, since they are moving, they have kinetic energy on an atomic scale. So kinetic energy, mass skills. What is the kinetic energy of a 44 kilogram cheetah running at 31 meters per second? So let's given an unknown values. Given that the mass of the cheetah is 44 kilograms and the speed of the cheetah is 31 meters per second. Now we need to list the unknowns. In this particular case, it's asking us what is the kinetic energy. So that's what we're looking for. Now we write the equation for kinetic energy. To simplify it there, K equals 1/2 mv squared. And we insert the known values in the equation and solve for the answer. In this case, we have K equals 1/2 times 44 kilograms, which is the mass, times 31 meters per second squared, which is the velocity or speed of the object. And that gives us 2.1 times 10 to the fourth kilograms times meters squared second squared, which is the same thing as a joule. And this ends up being 21 or 2.1 times 10 to the fourth is 21,000. So we have 21,000 joules is the kinetic energy of the cheetah. Other forms of energy. So what is non-mechanical energy? Now, energy that lies at the level of the atom is sometimes called non-mechanical energy. And non-mechanical energy is basically the amount of work that an object can do because of the object's kinetic and potential energy. So non-mechanical energy doesn't involve kinetic and potential energies listed in the objects. In most cases, non-mechanical forms of energy are just special forms of either kinetic or potential. Alright, chemical reactions. Those involve potential energy. The amount of chemical energy associated with a substance depends in part on the relative positions of the atoms it contains. And because you're going to have atoms moving around in chemical reactions, you get energy from that. Living things get energy from the sun. Plants use photosynthesis to turn energy into sunlight into chemical energy, and the sun gets its energy from nuclear reactions. It's fueled by the nuclear fusion reactions in its core. Energy can also be stored in fields. Electrical energy results from the location of charged particles in an electric field. We'll get to more of that in chapter 17. And when electrons move from an area of high electric potential to an area of low electric potential, they gain energy. So they're moving there. They have kinetic energy. Light can carry energy across empty space. Light energy travels from the sun to Earth across empty space in the form of electromagnetic waves. And electromagnetic waves are made of oscillating electric and magnetic fields. So light energy